The next topic is the importance of sequential design in material discovery by Torbo Lokman. Torbo Lokman has worked in Los Alamos National Laboratory for about 20 years. He has done intensive research in the area of condensed matter physics and computational material science. His authored and co-authored publications have been signed more than 14,000 times with H-index 59. Welcome.
Okay, next page. Okay, this one. Okay.
Thank you very much. Indeed, I think I need to speak in the mic, huh? Yeah. So I'm really happy to be back in China and talking at this meeting. I do remember the first meeting that I went to in 2017 when Professor Tong Yi was the chair of the meeting, and it's very nice to be back. Of course, at that time, the meeting was in a relatively small room, and so clearly much has happened since then. So it's very nice to see. So here is an outline of my talk. What I want to address today is the issue of materials design, and in particular, sequential design. How do we make decisions in sequence after we learn some new information? And what I want to sort of suggest is we've been using an approach for a number of years, and it's an approach that has been useful, but there are some issues related to it. And so I want to discuss those, and then I want to suggest how we can use another approach, more in the spirit of an AI-based approach based on reinforcement learning, to do compositional design. In this particular case, I'll give you an example of compositional design as it relates to alloys. So that's the scope of what I'm going to tell you. Okay, so let's start from the beginning. Let me give you some context. Making decisions is really the key. The question is, what is the optimal way to make decisions as you learn more information about the system that you are studying? And of course, this whole area has many intersections and overlaps, and it's important in many areas of science and engineering. In computer science, of course, machine learning, reinforcement learning, the whole business of sequential learners. In engineering, optimal control, and resource allocation. In mathematics, again, the mathematics of optimal control. And here you have operations research, which is really an applied area dealing with resource allocation, scheduling, etc. Real-world problems are really dealt with a lot of these tools. In neuroscience, how does the human mind work? How does the human mind make decisions? In psychology, conditioning, and economics, game theory, utility theory, the whole business of the usefulness of making rational decisions. So this is really an important area, and as you can see, all the tools overlap, and they're all used in these different areas. Okay, so there are certain techniques that are the core, and as you can see from this very nice illustration by Warren Powell, what we have are essentially 7 areas that have been studied and have evolved in their own right. But of course, as we learn more, as problems become more interesting, there is overlap between them. So the whole business of multi-arm bandits, exploration, exploitation tools that I will say something about, that's typically used in Bayesian global optimization, and reinforcement learning, lots of tools here, all part of what's called stochastic optimization. And there's a lot of overlap. And so one of the things I'm going to do today is to show you how we can use reinforcement learning as a means to perform compositional design. What I have been talking about in the past is how we can use some of these multi-arm bandits tools. So that's really the direction that I'm going to kind of go into. Okay, so what is the question? We all know that the issue is lab experiments are very limited. We have small amounts of experiments. There are uncertainties in the data. And of course, the key question is, how do we optimize, how do we perform experiments with a view to optimizing their usefulness, what is, the so-called utility of an experiment. And of course, you have to capture that in some measure that you will monitor, that will tell you, that you will optimize, you will maximize, that is going to tell you, hey, perform this experiment in the next step. Thereafter, as you learn information, perform the following experiment in the next step or computation. So that is really what this is about. And of course, the way that I got into this was about 2012. We submitted a proposal. The second time we got funded, and that allowed me, this was at Los Alamos, to basically undertake this task, which was to let's use some of these tools to do materials design. How do we guide the next experiments? Not by merely taking our knowledge, forming descriptors, making models, and just making predictions that you go and validate through computation experiments, not just doing that, but how do you essentially go and feed that information back and simplify and do the learning process, which means you need to know about uncertainties and how do you make decisions, the whole area of adaptive experimental design. So this is really a big area in statistical inference. A lot of people have been studying this for many, many years, but it's one of the things that we noticed. We noticed that we need these tools in material science. And so this is how this work started in about 2013 or 14. And of course, as we discovered, industry has very much been at the frontier. They've been miles ahead. Many of these problems are real. Industry has been studying them, and some of the major advances, as I will show you, have been due to people, researchers working in industry, in particular places like Ford, for example. So the whole business of understanding the value of information, this was something that was studied by Howard in '65 when he asked questions about the probabilistic assessments related to economic data and how do you sort of make, how do you make decisions? The whole business of utility functions. How do you encode the valueness, the value associated with doing an experiment? And he was, in fact, able to rationalize a lot of this thinking and came up with the Bayesian global optimization scenario as we understand it today. The business of improvement, defining an improvement was something that Kushner studied in the context of functions that are unknown. You don't really know much about them except that they're continuous, smooth. But how do you find optima of various functions based on these notions of improvement from the best so far? This is really the context. And of course, some other new ideas. And industry, of course, has been using these because a lot of these codes in industry are very complex. You can't just go and search the whole space. It's just too costly. There are high-value regions, low-value regions. You've got to take your resources and you have to put them to use in a strategized way so that you minimize the number of experiments that you need to do, or computations, of course. So that is the kind of literature that was already there that we learned from. And of course, one of the things we did was to use that information and try to start applying it to alloys, do experiments, synthesize them, and so we came up with this. So we gave ourselves the task of doing it for systems that we understood, like shape memory alloys, nickel titanium-based shape memory alloys. Here we were interested in finding a composition that had the smallest hysteresis. And so this was one of the first successes that we had, where we showed, yes, we could find compositions better than the best that we had available at that time, better than the best available data at that time, in a principled way, where we suggest experiments, we go synthesize the materials, we go feed that information back so that we then modify what we should do next, etc. And then, of course, we and many others have proceeded to apply these tools to many other problems. So this is barium titanate, trying to look for materials with large strains. And then, of course, we started to also study the different strategies experimentally. In other words, use different strategies, different ways of choosing an experiment, and then follow that particular strategy and find some commonalities. This, of course, and the community has been using this. We've been using it for a number of different types of problems. So that's all in the past, and it's interesting and good. And of course, these are the very methods that are now being used in self-driving experiments. So as you know, there's a lot of interest in doing a lot of these experiments in an autonomous, automated way. And of course, as we know, that's all very well, but for alloys, these experiments are hard to do. We cannot do these experiments. I just want to, this is the work going to some of these papers that have been published. It's very interesting to sort of run one of these movies to see what a self-driving lab involving a robot can look like, where a robot basically is controlled and performs experiments in order, one after another over a weekend as, you sleep, and then it collects all the data, etc. So, this is the way things are happening. And as I know, a number of labs in China are now starting to come up with various schemes to automate various types of syntheses. But of course, alloy design is still far away from that. Okay, we will stop this and keep proceeding. Okay, so what is the issue? So this is the typical basic loop. And of course, what you have to do, the way that this loop works is you have some utility of doing the experiment, some measure. It can be expected improvement. It can be upper confidence bounds, many, many things. You can choose what you like. And what you typically do is you rank all the possibilities in the candidate space, the search space that you have. And of course, that space can be very, very large. If I have 4 components, it can be 10 to the 8. If I have 10 components, it can be 10 to the 18. That can be very large. And so what you have is an explosion of that total space, because you need to know the outcome. You need to know the labels using some model that's fitted to the data. You need to know what the labels are before you make a decision as to what experiment you should do next. But if that space becomes very large, what are you going to do? That's a question. Also, you're only looking at the current step, one step. What if you want a strategy that allows you perhaps to look at a lot more steps? And of course, a very important question is, in what we've been doing, as I will illustrate with some examples, what is this? There's no stopping criteria. We typically stop when we run out of money, no more budget, or we are happy with what we have. So that's... Okay, I should speak in the mic. Okay, we typically run out of money, then we stop. So the stopping criterion is a very, very important element of trying to find some strategy that will work for us. So one of the things before I go there, so let me show you some of the issues that we typically have. So these are examples of work I've been involved in, and also other people's work, where again, here. Is this a pointer? Yeah. Again, you see, this is sort of the expected improvement, and you can see it goes down so that you're making progress, and then, you're finding materials that are not as good as the ones you've already had, but then the improvement is quite large. Similarly here, the measured data is rather low, but the improvements are large, etc. So there are issues in deciding, in finding a good stopping criterion. And the best that we can do is really for very, very simple things, like a 1D curve, for example, 1D fatigue curve, where the objective is fairly straightforward and the optimization is very clear-cut. So for some of these things, it works reasonably well, but it doesn't work well in general. So that's an issue that one needs to look at. Okay, so this is basically the loop that we have so far. And so what the collaboration that I will now show you has done is to examine another way of doing this, another way of essentially suggesting the experiments you should do. What we should do is to essentially have an inner loop where we learn, where we have an agent that is going to do by trial and error and learn. And essentially, it's going to learn, hopefully quickly, efficiently, and tell you what are the experiments you should do. I don't want to just sit there and rank all my candidates and decide based on some measure of the usefulness of doing that experiment. I want an agent to tell me what is the next thing, what are the next experiments I want to do. So that is the proposal. We will use a trained agent that's trained in going around and navigating this search space. So this is a bit more specific. So we'll have essentially a reinforcement inner loop where we have some kind of model that's been trained on the data that you have available. That will essentially be our reward, if you like. That'll be a measure of the reward that the agent is going to learn from. The agent has an environment, the space it already has, in which it's going to sample. And then after it samples that space, it chooses a state. It will then take some action. It will go and tell you, hey, this composition is no good. Let's change this to that. That's the idea. And we want to do that inner loop. And then after it's trained, we then will go and propose the experiments. So it's an agent-based learning process to perform the next experiments. That's the difference now between what we were doing before. So now I have to tell you how practical this is. So now the loop, the active learning loop, and I still have to show you that it's active learning. The active learning loop are these new arrows. So they are basically going to go and do the active learning. We're going to have an agent, an AI agent that is going to do the learning for us. We don't want to kind of take upon us to do we're not even learning so far. We're just sort of ranking. Ranking is kind of a passive way to learn, but we're not sort of learning. Okay, so what is the problem that I have to tell you? What is the problem we're going to look at? We're going to look at solid-solid phase change materials. These are important materials in essentially allowing you to shift thermal loads, especially under extreme conditions of temperature, etc. And you need some of these for things like high-temperature semiconductors working at 200 C. You need materials that will allow you to absorb and dissipate energy very, very fast so that you can shift the thermal loads. And nickel-titanium group of compounds are very good at this because they have relatively large thermal, large latent heats or enthalpies. And if you look at this picture, they certainly are very, very competitive insofar as where they stand compared to, this is the figure of merit, which is the enthalpy times the thermal conductivity times the specific density. And so here's a figure of merit. And they're certainly better than a lot of the solid liquid materials, also metals and oxides and so on. And so we said, okay, let's try and see what we can do with these particular alloys insofar as trying to find really good solid state phase materials. So here is this inner loop that we are going to perform using reinforcement learning. Okay, so here is this inner loop that I've been talking about. And here is the state, the agent, the action. And here's the outer loop, which is going to be the experimental loop only when the agent is trained. So we basically start off with a composition, and we are going to perform the action. So the state is the composition, okay? And we're going to perform some action. The action is going to be based on some reward. And the reward is essentially the difference between should you choose to be in that state, new state, compared to the old state. It's really the difference in the, if you like, the rewards between those two states. So that's what you mean by reward. I don't have a way of asking the reward from the experiment. I can't do that. The alloy isn't going to tell me, here's your reward. I have to define a reward. And so this is a model-based reward using the data we already have. So here is that inner loop, and this is a typical trajectory, if you like. We do a substitution of nickel, copper, hafnium, zirconium into the parent compound. And at each stage, as you do the substitution, you get a new state. You're sampling a new state. You have new rewards if that state is a good state or not. You take certain action. The action is basically changing the composition of a given component. And of course, the compositions can vary. Depends on the discretization that you allow for and the synthesis and experiments you can do. So very, very simple way to formulate the compositional design strategy. And in fact, this strategy should be very, very good for processing conditions because they go in sequence. That's the nice thing about this scheme. And here's a typical way, an episode is basically going through these four steps here. And so this is the enthalpy as the agent starts to learn. This is the enthalpy as a function of training episodes, as it keeps going around this loop, inner loop sampling. And you can see very, very quickly, it finds the best reward. What the agent is doing is getting the best cumulative reward for the problem. And I don't know how much you know about reinforcement learning, but the whole idea of reinforcement learning is to maximize the cumulative reward, okay? The inner reward plus the reward of all other states. And the way we do it typically is using this simple Bellman relationship because it allows us to express the value of being in that state in terms of the value of being in the next state, because this next state is doing everything following that state, etc. So it's a very simple recursion that allows us to very easily calculate the values of states as well as the Q values associated with not just the value of the state, but also the action that you need to take. So it's a very simple scheme, and typically what you have is a table. So if I don't have a big problem, if I don't have a big search space, then I essentially have a table that tells me what are the states, what are the actions that I can take, and you're basically going to choose the action which will maximize, which will have the biggest Q value. That's basically all you're doing. Now, if I have a small enough space, I can do this by hand. I can do it in a Q table. But if I have huge possibilities, I use an approximator. So the approximator is a neural network. And in this game, the approximator is basically a deep neural network. And so this is where deep Q learning comes from. So essentially what this does is, given a state, it essentially tells you all the Q values associated with the actions. And the system will choose the action with the largest Q value. Very, very simple. Very, very simple. And that's what you basically go and do. And you can see now it's very, very stable and highly efficient. These are different runs with different random numbers. And you can see that the agent very, very quickly learns. So here we have a sequential order in the way that we will choose the various compositions, the components, I should say. But if you allow the agent to just go and choose the compositions, the components randomly, it takes a bit more time to learn. The agent has to learn. So there's a lot more fluctuations involved. But it very, very quickly goes and finds the largest cumulative reward. That's what you are really waiting for. And so it then basically, there's a state associated with that cumulative reward. It's the compositions. So here, for example, is the trajectory as the agent learns. These are the compositions of the alloy. And you can see initially the compositions are fluctuating a bit. They're not settled. And then you settle into the compositions the agent tells you, go and do the experiment using. And here is an example of starting from some composition, so some alloy, and you can see how the composition of hafnium in this case sort of is zero, and then suddenly at the 7th iteration, experimental iteration, it becomes non-zero. So you can follow how the agent is choosing the composition. It gives you a window into the whole process. It's very, very insightful. So what are the results? So these are the results that we get, and you can see we start off with this initial data, and you can see that initially the agent proposes an experiment, and then we propose three other additional experiments based on the agent, the Q table that the agent has learned. And you can see that the proposed experiments initially are not very good. They're worse than the initial data set. That's because the agent is learning. This is the learning process. As the agent starts to learn, it has learned better and better, and then it goes to the maximum cumulative reward, and it proposes experiments that are really good. You can see that this is very beautiful active learning. Here is the root mean square as a function of iteration number, experimental iteration number, and you can see that it very nicely goes down. Successive experimental, new experiments are all consistent with that model. And the nice thing here is that the reward model is also being iteratively improved as the agent is iteratively learning. So that's sort of highly cumulative in this sense. Okay. Now, I can change the definition of reward. My reward doesn't always have to be the best. I'm going to make expected improvement a reward. I want the agent to maximize the expected improvement. So here now is a situation where I'm using expected improvement not just for my next state, but for future states as well, because that's how the reward hypothesis, that's how reinforcement learning works. And you can see that if expected improvement is highly efficient, okay? It's highly efficient compared to just going for the best, the mean, or even a UCB. So expected improvement, maximizing the expected improvement is really seems like a very good reward. Because remember what expected improvement has. It's a way of introducing uncertainty in the mean value. Now, this is a very interesting plot. So this is a plot of this enthalpy that the agent has proposed as a function of experimental iteration number. Now, I had told you that we really couldn't understand a lot of the profiles that we would get from many other studies. And you can see that this is also very interesting because what's happening is expected improvement goes down and then it goes up. Why? I told you that the agent needs to learn. And this agent is learning initially up to about 4 iterations. And all it's doing is that it's just going and suggesting experiments. The uncertainties are not large. It's just suggesting experiments to maximize the expected improvement. But that isn't very large. So the expected improvement is just decreasing. It's just a learning process. But once it has learned, it starts to explore more. The uncertainties start to get larger and expected improvement starts to get larger as the agent starts to learn more and tries to monotonically, the agent predictions are monotonically smoothing out. Now, one of the nice things about a strategy like this is, for alloys in particular, you have a lot of existing data. A lot of people have spent a lot of time generating data. Wouldn't you like to take that data and already pre-train the agent so that the agent doesn't have to spend a lot of time learning initially? That's precisely what is done here. So you see, if you don't pre-train the agent, the red curve is the trajectory you follow in the sampling. If you pre-train, the agent starts off already from a state that is higher. And you see this very, very well in these TSNE plots. What you're seeing is the frequency. So this is the frequency difference between pre-training and no pre-training in compositional space. So all of this is the compositional space that you're seeing. And what you're seeing here is the enthalpy. So the red are the areas of large enthalpy. That's where the rewards are larger. You can see that this is precisely where you want to be, because with pre-training, you can see that that's the region where the rewards are larger compared to no pre-training. So pre-training really helps the agent to learn and seek out higher frequency, seek out regions of higher frequency visits. Now, it's all part of the efficiency. How efficient is this compared to the way we normally do Bayesian global optimization by ranking? That's the key question. Now, the efficiency here is measured in terms of how many times do you have to call the surrogate model. If you're doing ranking, then you have to call the surrogate model. If you have a candidate space of n, you have to call it n times. But if you are not ranking, you can see that it's much, much faster. So this is a much more efficient system, a much more efficient algorithm than the Bayesian optimization. And finally, I have to tell you how good are these materials that we found using this scheme. So you can see that these are the materials that we found, which are very, very competitive in the whole world, in the whole class of materials, compared to what has been available as far as these solid phase materials are concerned. So these are these nickel titanium based alloys that we have been using for this particular study. So finally, let me suggest the following, that this particular agent-based approach shows promise. It shows promise. We've applied it to guide us in finding new compositions. Of course, we're doing various other things, including learning how we can apply them to processing conditions, etc. And here is a very nice, interesting question. Can I already use the trained agent, my Q table, as a means, as a starting point to already predict new chemistries which are not incorporated so far in what I have shown you? That's a very good question. These are all the collaborators I need to thank, first and foremost. They all worked on this project. And there is a poster, if you would like to know more about this work, there is a poster by Yui Xian, one of our excellent students at Xian Jiaotong, and he's got this poster, and so you can learn more in there. Thank you.